Good morning, students. Welcome to the fourth lecture on solutions. So, in our previous chapter, we have discussed about solubility. Solubility of a solution in which solute as solid and solute as gas we have discussed. The factors that affect the solubility of a solid in a liquid, and then the factors that affect the solubility of a gas in liquid we have discussed. And then we also discussed about Henry's law. So, as per Henry's law, at constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas above the solution. Or, in other words, the partial pressure of the gas above the solution is directly proportional to the mole fraction of the gas in the solution. Its mathematical form also we have discussed. So today in our session, let us discuss few numerical problems based on that, and then we will continue with the topic. Okay, so let me take the first problem. So, according to the first problem given here, if a nitrogen is bubbled through water at 293 Kelvin, how many millimoles of nitrogen gas would dissolve in 1 liter of water? Assume that nitrogen exerts a partial pressure of 0.987 bar, given that Henry's law constant for nitrogen at 293 Kelvin is 76.48 kilobar. Okay, so we have to find out the millimoles of nitrogen gas that would dissolve in 1 liter of water. In the sense, we have to find out the solubility of nitrogen gas in millimoles. ಅಲ್ವಾ ಸೊ ಏನೆಲ್ಲ ಕೊಟ್ಟಿದ್ದಾರೆ ಪ್ರೆಷರ್ ಕೊಟ್ಟಿದ್ದಾರೆ ಪ್ರೆಷರ್ ಇಟ್ ಹ್ಯಾಸ್ ಬಿನ್ ಮೆನ್ಷನ್ಡ್ ಆಸ್ 0.987 bar. So partial pressure is given ಅಲ್ವಾ ಆ ನಂತರ ಏನ್ ಕೊಟ್ಟಿದ್ದಾರೆ Henry's law constant has also been given. So Henry's law constant ಅಂತ ಹೇಳಿದ್ರೆ KH ಅಲ್ವಾ KH ಕೂಡ ಕೊಟ್ಟಿದ್ದಾರೆ. So from the Henry's law we have P is equal to KH into X alva. So according to Henry's law, what does it say? It says that the partial pressure of the gas above the solution is directly proportional to its mole fraction in the solution alva. So P is equal to KH into X anta namge gottuntu. So namige iga we have to find out the mole fraction. ಆ ನಂತರ number of moles ಅನ್ನ ಏನಲ್ಲಿ millimoles ಅಲ್ಲಿ ನಮಗೆ we need. Okay, so from this equation we can write X to be equal to P by KH alva. K because we need X, so take KH to the other side, so it will go to the denominator. So we have X is equal to P into KH. So now substitute the values. P is equal to H2, P is 0.987, so 0.987 divided by KH, sorry. So it is 76.48 kilobar anta untu. So this has to be kilobar. Okay, so it is 76.48 into 10 to the power 3. Okay, so now, so that comes out as 1.29 into 10 to the power minus 3 mole fraction, so no unit. Alva? And now we need the solubility in terms of millimoles of nitrogen. Alva? So what is mole fraction? Mole fraction is number of moles of nitrogen divided by number of moles of nitrogen plus number of moles of H2O, I mean water. Therefore, moles of we need to calculate number of moles of water, and then we need number of moles of nitrogen. So number of moles of water, if we calculate, it is 1 liter has been given. So So it is 1000 gram divided by 18. So it will come as 55.55. So now, therefore, find out the value of N. So x is equal to N divided by N plus 55.5. Therefore, x is equal to mole fraction of nitrogen is 1.29 into 10 to the power 3. Alva substitute ಮಾಡಿ. So we will get, if we substitute, we will get 0.716 millimole. Millimole ಅಲ್ಲಿ ಬೇಕಿದೆ, ಮೋಲ್ ಸಿಗ್ತದೆ ಅದರಲ್ಲಿ. ಸೊ ಅದನ್ನ ಮಿಲಿಮೋಲಿಗೆ ಕನ್ವರ್ಟ್ ಮಾಡಿದ್ರೆ ಆಯ್ತು. ಸೊ ಇಟ್ ವುಡ್ ಐ ಮೀನ್ 10 to the power 3 ಇಂದ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಬೇಕು. ಸೊ ನಮಗೆ ಅದು it comes out as ಇಲ್ಲಿ 10 to the power minus 5 ಬರುತ್ತೆ ಆಯ್ತಾ. So this comes out as 10 to the power minus 5. So that is one small mistake, small error over here. ಅದನ್ನ ನೋಡ್ಕೊಳ್ಳಿ. Okay, so it comes out as 0.716 millimole. Okay. Yeah, so let me take up one more problem. So Henry's law constant for the molality of methane in benzene at 298 Kelvin is 4.27 into 10 to the power 5 mm of mercury. Calculate the solubility of methane in benzene at 298 Kelvin under 760 mm of Hg. So here the solubility has been asked. Solubility in ಹೇಳಿದ್ರೆ you can keep it in millifraction directly because they have not mentioned to they have not asked to find out in write in terms of moles, millimoles, nothing. So we can keep it in the mole fraction itself. Okay. So yes, the formula is P equal to KH into X. So what we need, first of all, Henry's law constant has been given. Henry's law constant for the molality of the methane in benzene is so much. Therefore, what is this? It is KH. Okay. Idu KH. Another calculate the molality of methane at 298 under so much 760 mm of mercury. Therefore, it is P. So P is known, KH is known. So we have to calculate the X. So X will be equal to P by KH. So substitute P is equal to 760 mm of Hg and KH is equal to 4.27 into 10 to the power 5 mm of Hg. So it comes out as 1.78 into 10 to the power minus 3. Okay, clear? I hope ಅರ್ಥ ಆಗಿದೆ ಅಂತ ಅನ್ಕೊಳ್ತೇನೆ. Okay. Yeah, so now let me move further. So in the previous class, ನಾವು ಏನು ಡಿಸ್ಕಸ್ ಮಾಡಿದ್ದೇವೆ? Solubility of gas ಅನ್ನ ನೋಡಿದ್ದೇವೆ. Solubility of solid in solid ಅನ್ನ ನೋಡಿದ್ದೇವೆ. So now ಇವಾಗ ನಾವು ಇನ್ ಒಂದು ಟೈಪ್ ಉಳ್ಕೊಂಡಿದೆ ಅಲ್ವಾ? ಯಾವ್ದದು? Solubility of liquid in liquid, solution of liquids in liquid, it is pending. So now let us discuss about that. Okay, so when we say liquid in liquid alva athwa in general liquid anta helidaga, say for example water is also liquid alva, water is also liquid. Anantra ether athava ethanol alva, that is also liquid. Diethyl ether ಅಥವಾ dimethyl ether ಅನ್ನ ನೋಡಿದ್ರೆ that is also liquid ಅಲ್ವಾ. ಬಟ್ ವಾಟ್ ಡಿಫರೆನ್ಸ್ ಡೂ ಯು ಫೈಂಡ್? ಏನ್ ಡಿಫರೆನ್ಸ್ ಇದೆ ಅದರಲ್ಲಿ ಈಥರ್ ಮತ್ತೆ ವಾಟರ್ ಅಲ್ಲಿ? ಈಥರ್ ಅಂತ ಹೇಳಿದ ತಕ್ಷಣ ಡೈಥೈಲ್ ಈಥರ್ ಅನ್ನ ತಗೊಂಡ್ರೆ ಅಥವಾ ಡೈಮಿಥೈಲ್ ಈಥರ್ ಅನ್ನ ತಗೊಂಡ್ರೆ ಅದ್ರದ್ದು ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಇಫ್ ಯು ಅಬ್ಸರ್ವ್, what is its boiling point? If you keep it open at the laboratory condition itself for a longer time, the whole bottle gets emptied. Okay. On the other hand, water, if you keep it open, it will remain as such because either the boiling point very less on the 40-45 degree ಗೆಲ್ಲ ಸಾಧಾರಣ almost ಅದು evaporate ಆಗಿ ಹೋಗಿ ಬಿಡ್ತದೆ. Okay. So what do you call such liquid? They are highly volatile liquid. ಅಲ್ವಾ? ಒಂದು highly volatile liquid water, I mean sorry ether, ಇನ್ನೊಂದು ಅಷ್ಟು volatile ಅಲ್ಲ, little ಸ್ವಲ್ಪ ಕಮ್ಮಿ. ವಾಟರ್ ಅನ್ನ ನೋಡಿದ್ರೆ ಈಥರಿಗಿಂತ ಇದು ಕಮ್ಮಿ volatile. ಸೊ ಲಿಕ್ವಿಡ್ ಅಲ್ಲಿ ಆ ರೀತಿ we can have two types of liquids. One is highly volatile liquid, ಇನ್ನೊಂದು non volatile ಅಥವಾ less volatile ಅಂತ ಹೇಳ್ಬೋದು. Okay, so ಏನಾಗ್ತದೆ, what exactly happens if you keep such liquid in a closed container? If you keep it open, the liquid, if liquid is very volatile one, then all the liquid will vaporize off and nothing remains. Okay, ಅದೇ ನೀವು ಒಂದು ಕ್ಲೋಸ್ಡ್ ಕಂಟೈನರ್ ಅಲ್ಲಿ ಅದನ್ನ ಇಟ್ರೆ ಏನಾಗ್ತದೆ, ಪಾರ್ಟಿಕಲ್ ಸರ್ಫೇಸ್ ಮೇಲೆ ಪಾರ್ಟಿಕಲ್ ಇದೆ ಅಲ್ಲ, ಅದು ದೇ ವಿಲ್ ಬಿ ಟ್ರೈಂಗ್ ಟು ಎಸ್ಕೇಪ್ ಔಟ್ ಆಫ್, ಬಿಕಾಸ್ ಪಾರ್ಟಿಕಲ್ ಗಳಿಗೆ ಅದರದ್ದೇ ಆದ ಒಂದು ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಇದ್ದೇ ಇರ್ತದೆ. ಸೊ ಅದರಿಂದಾಗಿ ಸೇ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ನಾವು ಫಸ್ಟ್ ಇಯರ್ ಅಲ್ಲಿ ಡಿಸ್ಕಸ್ ಮಾಡುವಾಗ ಸಹ ನಾವು ಒಂದು ವಿ ಹ್ಯಾವ್ ಡಿಸ್ಕಸ್ಡ್ ಏನು ಫಸ್ಟ್ ಇಯರ್ ಟಾಪಿಕ್ ಅಲ್ಲಿ ಎಂಟ್ರೋಪಿ ಬಗ್ಗೆ ಎಲ್ಲ ಡಿಸ್ಕಸ್ ಮಾಡುವಾಗ ಆಲ್ ದ ಸಬ್ಸ್ಟೆನ್ಸ್ ಆಲ್ ದ ಸಿಸ್ಟಮ್ ದೇ ಹ್ಯಾವ್ ದ ಟೆಂಡೆನ್ಸಿ ಟು ಗೆಟ್ ಇನ್ ಟು ದ ಡಿಸಾರ್ಡರ್ ಅಲ್ವಾ, ದಟ್ ಟೆಂಡೆನ್ಸಿ ದಟ್ ವಿಲ್ ಬಿ ದೇರ್. ಸೊ ಅದೇ ರೀತಿ ಇಲ್ಲಿ ಕೂಡ ಏನು ಮಾಲಿಕ್ಯೂಲ್ಸ್ ದೇ ಹ್ಯಾವ್ ದ ಟೆಂಡೆನ್ಸಿ ಟು ಎಸ್ಕೇಪ್, ಆ ಒಂದು ಇದು ಇದ್ದೇ ಇರ್ತದೆ. Okay, but along with that, there also exists attraction among the particles. Also, interparticle attraction ಕೂಡ ಇದ್ದೇ ಇರ್ತದೆ. ಸೊ ಅದು ಯಾವ ಕಂಡೀಷನ್ ಅಲ್ಲಿ ಇರ್ತದೆ ಅಂತ ಹೇಳುವಂತದ್ದು ಡಿಪೆಂಡ್ಸ್ ಅಪಾನ್ ದ ಬ್ಯಾಲೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದೀಸ್ ಟು ಅಪೋಸಿಂಗ್ ಫೋರ್ಸಸ್. ಆಯ್ತಾ? ಸೊ ಆ ರೀತಿ ನಾವು ನೋಡಿದ್ರೆ ಏನಾಗ್ತದೆ, ಒಂದು ಕ್ಲೋಸ್ ಕಂಟೈನರ್ ಅಲ್ಲಿ ಪಾರ್ಟಿಕಲ್ಗಳು ಇರುವಾಗ, ಲಿಕ್ವಿಡ್ ಅಂದ್ರೆ ವೊಲಟೈಲ್ ಲಿಕ್ವಿಡ್ ಇರುವಾಗ ಏನಾಗ್ತದೆ, ಆ ಸರ್ಫೇಸ್ ನಲ್ಲಿರುವ ಪಾರ್ಟಿಕಲ್ಗಳು, ಆ ಸರ್ಫೇಸ್ ನಲ್ಲಿರುವ ಪಾರ್ಟಿಕಲ್ಗಳಿಗೆ ಕೆಳಗಿಂದ ಇರುವ ಪಾರ್ಟಿಕಲ್ಗಳು ಅದನ್ನು ಪುಲ್ ಮಾಡ್ತಾ ಇರ್ತದೆ. ಅದೇ ರೀತಿ ಇಟ್ ಇಟ್ ಸೆಲ್ಫ್ ಹ್ಯಾಸ್ ದ ಟೆಂಡೆನ್ಸಿ ಟು ಎಸ್ಕೇಪ್ ಔಟ್ ಆಫ್ ದ ಸಿಸ್ಟಮ್. ಸೊ ಅಲ್ಲಿ ಕೆಲವು ಪಾರ್ಟಿಕಲ್ಗಳು ಮೇಲೆ ಹೋಗ್ತದೆ, ಅಂದ್ರೆ ವೆಪರೈಸ್ ಆಗಿ ಗೇಷಿಯಸ್ ಫಾರ್ಮಿಗೆ ಹೋಗ್ತದೆ. ಅದೇ ರೀತಿ ಇನ್ನು ಕೆಲವು ಪಾರ್ಟಿಕಲ್ಗಳು ಲಿಕ್ವಿಡ್ ಅಲ್ಲಿ ಅಥವಾ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ ಇರ್ತದೆ. ಓಕೆ, ಸೊ ದೇರ್ ಎಕ್ಸಿಸ್ಟ್ ಅ ಡೈನಾಮಿಕ್ ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಬಿಟ್ವೀನ್ ದೀಸ್ ಟು, ಐ ಮೀನ್ the particles in the vapor phase and particles in the solution phase. Okay, so because of this, pressure will be exerted by the vapors of the, so ಇದು ಏನ್ ಮೇಲೆ ಹೋಯ್ತು ನೋಡಿ, ಅದು ಪಾರ್ಟಿಕಲ್ಗಳು ಈ ಕೆಳಗೆ ಇರುವ ಪಾರ್ಟಿಕಲ್ಗಳೊಟ್ಟಿಗೆ ಒಂಥರ ಕೆಳಗಿರುವ ಪಾರ್ಟಿಕಲ್ಗಳು ಅದನ್ನು ಎಳಿತಾ ಕೂಡ ಸಹ ಇರ್ತದೆ. ಓಕೆ, ಸೊ ಅಲ್ಲಿ ಬಿಕಾಸ್ ವಿ ನೋ there exists a interparticle attractive force also, and similarly the particles will also be having the tendency to get out of that. Okay, so because of such two opposing forces, the pressure will be exerted by the vapors of the liquid in equilibrium liquid phase at the pressure exerted by the vapors of the liquid in equilibrium with the liquid at some constant temperature. Okay, so the pressure exerted by the molecules of the vapor phase on the liquid phase at equilibrium is called as the vapor pressure. Clear? So what is vapor pressure? The pressure exerted by the molecules of the vapor phase on the liquid phase at equilibrium is called as equilibrium vapor pressure, or simply it is called as the vapor pressure. So ಈ ಪಾರ್ಟಿಕಲ್ಗಳು ಯಾವುದು gaseous phase ಅಲ್ಲಿ ಇದೆಯೋ they will be exerting kind of pressure on the liquid phase. So that pressure, so when it is at equilibrium, the pressure that is exerted by the particles in the vapor phase onto the liquid phase is called as the vapor pressure of the solution. Clear? So now let us discuss what are the factors that influence the vapor pressure. I hope vapor pressure is clear to you. So vapor pressure ಅಂದ್ರೆ ಏನು, ಲಿಕ್ವಿಡ್ ಸಾರಿ ವೇಪರ್ ಫೇಸ್ ಅಲ್ಲಿರುವ ಪಾರ್ಟಿಕಲ್ಗಳು ಲಿಕ್ವಿಡ್ ಫೇಸ್ ನಲ್ಲಿರುವ ಪಾರ್ಟಿಕಲ್ಗಳ ಮೇಲೆ, ಆ ಲಿಕ್ವಿಡ್ ಸರ್ಫೇಸ್ ಮೇಲೆ ಒಂದು ಪ್ರೆಷರ್ ಅನ್ನ ಎಕ್ಸರ್ಟ್ ಮಾಡ್ತಾ ಇರ್ತದೆ, ಪ್ರೆಷರ್ ಅನ್ನ ಹಾಕ್ತಾ ಇರ್ತದೆ. ಸೊ ಆ ಪ್ರೆಷರ್ಗೆ ಅಟ್ ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಅಲ್ಲಿ ಇರುವಾಗ ಆ ಪ್ರೆಷರ್ ಏನ್ ಎಕ್ಸರ್ಟ್ ಮಾಡ್ತದೋ ಅದನ್ನ ನಾವು ವೇಪರ್ ಪ್ರೆಷರ್ ಅಂತ ಹೇಳ್ತೇವೆ. ಕ್ಲಿಯರ್? ಎಸ್, ನೌ ಲೆಟ್ ಅಸ್ ಡಿಸ್ಕಸ್ ಅಬೌಟ್ the factors that influence the vapor pressure. So as usual, one of the factor is nature of the solvent. So here now we are discussing about the same particles in solution phase and same particles in the solvent phase. Ade liquid aita, ade particle ಸೊಲ್ಯೂಷನ್ ಫೇಸ್ ಅಲ್ಲಿ ಕೂಡ ಉಂಟು, ಲಿಕ್ವಿಡ್ ಫೇಸ್ ಅಲ್ಲಿ ಕೂಡ ಉಂಟು. ನಾವು ಬೇರೆ ಏನನ್ನು ಆಡ್ ಮಾಡ್ಲಿಲ್ಲ ಈಗ ಸದ್ಯಕ್ಕೆ. ಸೊ ಆ ತರದಕ್ಕೆ ಆಯ್ತಾ, ಅಥವಾ ನಾವು ಎರಡು ವೊಲಟೈಲ್ ಲಿಕ್ವಿಡ್ ಅನ್ನೇ ಮಿಕ್ಸ್ ಮಾಡಿದಾಗ ಆಗ ಕೂಡ ಅದು ಇದೇ ರೀತಿ ಇರ್ತದೆ. ಎರಡು ವೊಲಟೈಲ್ ಲಿಕ್ವಿಡ್ ಅನ್ನ ಮಿಕ್ಸ್ ಮಾಡಿದ್ರೆ ಎರಡು ಪಾರ್ಟಿಕಲ್ ಗಳಿಗೂ ವೇಪರ್ ಫೇಸ್ ಗೆ ಹೋಗುವಂತ ಇದು ಟೆಂಡೆನ್ಸಿ ಕೂಡ ಇರ್ತದೆ. ಅದೇ ರೀತಿ ಸೊ ಅದರಿಂದಾಗಿ ಒಂದು ಕೈಂಡ್ ಆಫ್ ಅಫಿನಿಟಿ ವಿಲ್ ಬಿ ದೇರ್ ವಿತ್ ದ ಲಿಕ್ವಿಡ್ ಫೇಸ್ ಪಾರ್ಟಿಕಲ್ ಆಲ್ಸೋ. ಸೊ ಬಿಕಾಸ್ ಆಫ್ ದಟ್ ಅಲ್ಲಿ ಆ ಪ್ರೆಷರ್ ಎಕ್ಸರ್ಟ್ ಆಗ್ತಾ ಇರ್ತದೆ. ಓಕೆ, ಯಾ. ಸೊ ನೌ ಲೆಟ್ ಮಿ ಮೂವ್ ಆನ್ ಟು ದ ಫ್ಯಾಕ್ಟರ್ಸ್ ಇನ್ಫ್ಲೂಯೆನ್ಸಿಂಗ್ ದ ವೇಪರ್ ಪ್ರೆಷರ್. So what are the factors that influence the vapor pressure? One of the factor is nature of solvent. So solvent having higher attraction among the molecule has less tendency to get vaporized. Correct alla? Particle ಗಳ ನಡುವೆ high attraction ಇದ್ರೆ ಆಗ can the particle get into the vapor phase easily? Vapor phase ಗೆ ಬೇಗ ಹೋಗ್ಲಿಕ್ಕೆ ನಾನು ಆಗ್ಲೇ ಹೇಳಿದೆ ಏನು, ಅಫಿನಿಟಿ, ಇಂಟರ್ ಪಾರ್ಟಿಕಲ್ ಅಟ್ರಾಕ್ಷನ್, ಅದೇ ರೀತಿ ಟೆಂಡೆನ್ಸಿ ಟು ಗೆಟ್ ವೆಪರೈಸ್, ಟೆಂಡೆನ್ಸಿ ಟು ಗೆಟ್ ಇನ್ ಟು ಡಿಸಾರ್ಡರ್ ಅಲ್ವಾ, ಅದು ಎರಡೂ ಕೂಡ ಕೋ ಎಕ್ಸಿಸ್ಟ್ ಆಗ್ತದೆ. ಬೋತ್ ದೀಸ್ ಅಪೋಸಿಂಗ್ ಫೋರ್ಸಸ್ ವಿಲ್ ಬಿ ಆಕ್ಟಿಂಗ್ ಸೈಮಲ್ಟೇನಿಯಸ್ಲಿ. ಸೊ ಈಗ ಏನು, ಇಫ್ ದ ಸಾಲ್ವೆಂಟ್ ಹ್ಯಾಸ್ ಹೈಯರ್ ಅಟ್ರಾಕ್ಷನ್, ಆ ಪಾರ್ಟಿಕಲ್ ಗಳ ನಡುವೆ ಅಟ್ರಾಕ್ಷನ್ ಜಾಸ್ತಿ ಇದ್ದಾಗ ಆಗ ಟೆಂಡೆನ್ಸಿ ಟು ಗೋ ಇನ್ ಟು ದಿ disorder will be less. Correct alla? So aga the molecule has less tendency to get vaporized. Vaporize aguva tendency kammi agtade. So how does it will affect the vapor pressure? So the vapor pressure will be less. So the system or the solution will have lower, or the liquid will have lower vapor pressure. Clear? How does the nature of the solvent influences the vapor pressure? So if the solvent has high attraction force, then the tendency to get into the vapor phase will be lesser. As a result, vapor pressure also will be lesser. Clear? Yes. So now, whereas solvents having weak intermolecular force will be, therefore, yes, they will be having low attractive force. ಅದರಿಂದಾಗಿ ಡಿಸಾರ್ಡರ್ಗೆ ಹೋಗುವ ಟೆಂಡೆನ್ಸಿ ಜಾಸ್ತಿ ಇರ್ತದೆ, ಅಂಡ್ ದೇರ್ ಫೋರ್ ದೇ ವಿಲ್ ಬಿ ಮೋರ್ ವೊಲಟೈಲ್. ಆಗ ವೇಪರ್ ಪ್ರೆಷರ್ ವಿಲ್ ಬಿ ಹೈಯರ್ ಅಲ್ವಾ. ಎಕ್ಸಾಂಪಲ್ ಫಾರ್ ದಟ್ ಇಸ್ ಆಗಡೆ ಹೇಳಿದಂಥದ್ದು ಯಾವುದು, ಈಥರ್, ಮಿಥೈಲ್ ಆಲ್ಕೋಹಾಲ್, ಅದಕ್ಕೆಲ್ಲ ವೇಪರ್ ಪ್ರೆಷರ್ ಇಸ್ ವೆರಿ ಹೈ. ಓಕೆ, ಸೊ ಅದೇ ನಾವೀಗ ಇಫ್ ಯು ಲುಕ್ ಎಟ್ DMA, dimethyl glyoxime ಎಲ್ಲ ನೋಡಿದ್ರೆ ಅದರದ್ದೆಲ್ಲ ವೇಪರ್ ಪ್ರೆಷರ್ ಇಸ್ ಲೆಸ್. ಕ್ಲಿಯರ್? ಈಥರಿಗೆಲ್ಲ ವೆರಿ ಹೈ. ಇಫ್ ಯು ಕೀಪ್ ಇಟ್ ಓಪನ್ ಅಟ್ say 40 degree, the whole bottle itself gets emptied because it has a higher tendency to get into the vapor form. Therefore, okay, yeah. So now the second factor that influence the vapor pressure is the temperature. Temperature ಇಂದ ಏನಾಗಬಹುದು ಗೊತ್ತೇ ಇದೆ. What happens? As the temperature increases, kinetic energy will increase ಅಲ್ವಾ. ಟೆಂಪರೇಚರ್ ಜಾಸ್ತಿ ಆದ್ರೆ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ, ಎನಿ ಸಿಸ್ಟಮ್ಗೆ ಕೈನೆಟಿಕ್ ಎನರ್ಜಿ ಜಾಸ್ತಿ ಆಗ್ತದೆ. ಕರೆಕ್ಟ್? ಈಗ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಬೆಂಕಿ ಬಿದ್ರೆ, ಯಾವೆಲ್ಲೋ ಇದ್ದೇವೆ, ಅಲ್ಲಿ ಬೆಂಕಿ ಬಿತ್ತು ಅಂತಂದಾಗ ಡು ವಿ ಸ್ಟೇ ದೇರ್? ನೋ, ವಿ ವಿಲ್ ಸ್ಟಾರ್ಟ್ ರನ್ನಿಂಗ್ ಫ್ರಮ್ ದಟ್ ಪ್ಲೇಸ್. ಯಾಕೆ? ನಮಗೆ ಅದು ಬಿಸಿ ಆಗ್ತದೆ, ನಾವು ಅಲ್ಲಿಂದ ಓಡ್ಬೇಕು, ಅದಷ್ಟೇ ಇರುದು ನಮ್ಮ ತಲೆಯಲ್ಲಿ ಅಲ್ವಾ. ಅದೇ ರೀತಿ ಪಾರ್ಟಿಕಲ್ ಗಳಿಗೆ ಕೂಡ ಒಂದು ವೇಳೆ ಆ ಸಿಸ್ಟಮ್ ಇದ್ದು ಟೆಂಪರೇಚರ್ ಜಾಸ್ತಿ ಆದ್ರೆ the particles will start, or they will be start running. I mean, their kinetic energy will start increasing. So therefore what will happen? Interparticle, ಆಗ ನಾವು ನನ್ನ ಫ್ರೆಂಡ್ ಬಾಮರಾಯ ಅಂತ ಹೇಳಿ ಕೂತ್ಕೊಳ್ತೇವಾ? ಇಲ್ಲ ಅಲ್ಲ. So the tendency of the particles to get vaporized increases. Okay, so vapor pressure of solvent also will increase. Clear? So as the temperature increase, the kinetic energy of the particle will increase, and hence tendency to get vaporized, the particle's tendency to get vaporized also will increase, and therefore we can say vapor pressure of the solvent will increase. Clear? So these are the factors. There are few other factors also like boiling point and all, but that is again in turn it is related to these two factors only. Okay, so these are the factors that influence the vapor pressure. So one is the nature of the solvent and the other one is the temperature. So if the solvent has lesser interparticle attractive force, in the sense weak intermolecular attractive force, then it will be more volatile, vapor pressure will be higher. If the interparticle attractive force is higher, then the particles will be less volatile and vapor pressure will be lower. And temperature, if you look at, as the temperature increases, the vapor pressure also will increase. Clear? Yes. Now, so scientist by name Raoult, he studied many such systems, many mixtures of volatile liquids, and he proposed one law called as Raoult's law. Okay. So what does this Raoult law state? So Raoult law states that the partial vapor pressure of each component, ಏನು ನಾವು ಒಂದೇ ಗ್ಯಾಸ್ ಇದ್ರೆ ಅದು ಪ್ರೆಷರ್ ಆಗ್ತದೆ. We have seen, you know it from our first year class discussions. When we have a mixture of gases, it is always called as the individual gas pressure. Every gas will contribute towards the pressure, and the contribution of each gas, individual gas, it is called as the partial pressure. ಅಲ್ವಾ? ಅದೇ ರೀತಿ ಇಲ್ಲಿ ಕೂಡ ನಾವು ಒಂದೇ ಸಾಲ್ವೆಂಟ್ ಇದ್ರೆ ಅದು ಒಂದೇ ಸಿಸ್ಟಮ್, ಒಂದೇ ಸಬ್ಸ್ಟೆನ್ಸ್ ಇದ್ರೆ ಅದು ಅಲ್ಲಿ ನಾವು ಪ್ರೆಷರ್ ಅಂತ ಹೇಳ್ತೇವೆ. when we have mixture of two or more components, then we make use of the term partial, right? Okay. So according to Raoult's law, the partial vapor pressure of each component in the binary solution, remember, we are dealing with the binary systems only. Binary system anta helidre enu, where we have only two components. One will be in lower quantity, one will be in higher quantity, alva? ಅದರಿಂದಾಗಿ ಒಂದು solute ಆಗ್ತದೆ, ಇನ್ನೊಂದು solvent ಆಗ್ತದೆ. Okay, so in such binary solutions of two volatile liquids, the partial vapor pressure of each component is directly proportional to its mole fraction in the solution. Clear? So what is it saying? In a binary solution of two volatile liquids, the partial pressure of each component is directly proportional to its mole fraction in the solution. So ನಮ್ಮ ಹತ್ರ ಎರಡು ವೊಲಟೈಲ್ ಲಿಕ್ವಿಡ್ ನ ಮಿಕ್ಸ್ಚರ್ ಇದ್ದಾಗ ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಪ್ರತಿ ಕಾಂಪೋನೆಂಟ್ ಪ್ರೆಷರ್ ಎಕ್ಸರ್ಟ್ ಮಾಡ್ತದೆ ಅಲ್ವಾ? ಸೊ partial vapor pressure of each component is proportional to other mole fraction in the solution. Clear? ನಾವು ಹೆನ್ರೀಸ್ ಲಾ ನೋಡಿದ್ದೇವೆ. ಹೆನ್ರೀಸ್ ಲಾದಲ್ಲಿ ಅದು ಡಿಸಲ್ಯೂಷನ್ ಆಫ್ ಅ ಗ್ಯಾಸ್ ಇನ್ ಅ ಲಿಕ್ವಿಡ್. ಕರೆಕ್ಟಾ? ಇಲ್ಲಿ ಇಟ್ ಇಸ್ ಅ ಮಿಕ್ಸ್ಚರ್ ಆಫ್ ಟು ವೊಲಟೈಲ್ ಲಿಕ್ವಿಡ್, ಅಂದ್ರೆ ಲಿಕ್ವಿಡ್ ಇನ್ ಅ ಲಿಕ್ವಿಡ್. ಕ್ಲಿಯರ್? ಸೊ ಇಲ್ಲಿ ಕೂಡ ಅದು ಸಹ somewhat similar only. ಸೊ ಇಲ್ಲಿ ಕೂಡ ಇಟ್ ಇಸ್ the statement is somewhat similar. Okay, so the partial vapor pressure of each component in the binary solution of two volatile liquid is directly proportional to its mole fraction of the component in the solution. ಹಾಗಾಗಿ we can say, ಈಗ ಸಪೋಸ್ ಇಫ್ ಟೂ ಕಾಂಪೊನೆಂಟ್ಸ್ ಆರ್ ಎ ಅಂಡ್ ಬಿ ಅಂತ ಅಂದ್ಕೊಳ್ಳಿ. ನಮ್ಮ ಹತ್ರ ಇರುವ ಮಿಕ್ಸ್ಚರ್ ಕಂಪೌಂಡ್ ಎ ಮತ್ತೆ ಕಂಪೌಂಡ್ ಬಿ, ಅಥವಾ ಲಿಕ್ವಿಡ್ ಎ ಮತ್ತೆ ಲಿಕ್ವಿಡ್ ಬಿ ಅಂತ ಆದ್ರೆ, ಅದ್ರದ್ದು ಎದ್ದು ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಪಿ ಎ ಅಂತ ಆದ್ರೆ ಪಿ ಎ ಶುಡ್ ಬಿ ಪ್ರಪೋರ್ಷನಲ್ ಟು ಎಕ್ಸ್ ಎ ಅಲ್ವಾ? ಹಾಗಾಗಿ ಅದೇ ಏನು ಮ್ಯಾಥಮ್ಯಾಟಿಕಲ್ ಫಾರ್ಮ್ ಅಲ್ಲಿ ಬರೆಯೋದಾದ್ರೆ ಪಿ ಎ ವಿಲ್ ಬಿ ಪ್ರಪೋರ್ಷನಲ್ ಟು ಎಕ್ಸ್ ಎ. So this implies if we remove the proportionality sign and consider the equality sign, then the equation becomes PA will be equal to some constant, and that constant will be PA naught into XA. Clear? So partial pressure of component A is equal to its partial pressure in the pure form, not in the sense it is in the pure form, okay, into XA, mole fraction of the component A. Clear? Similarly, so if there are two components, say XA, A and B, and if their mole fraction in the solution is XA and XB, then according to Raoult's law, partial vapor pressure of the component A will be PA equal to PA naught into XA. Correct alla? ಅದೇ ರೀತಿ partial vapor pressure of component B will be PB equal to PB naught into XB ಅಲ್ಲ. ಸೊ ಆದ್ರೆ ನಮಗೆ ನಾವು ಫಸ್ಟ್ ಇಯರ್ ಅಲ್ಲಿ ನೋಡಿದ್ದೇವೆ ಏನು ಡಾಲ್ಟನ್ಸ್ ಲಾ. ಡಾಲ್ಟನ್ಸ್ ಲಾ ಏನ್ ಹೇಳ್ತದೆ, ಅಕಾರ್ಡಿಂಗ್ ಟು ಡಾಲ್ಟನ್ಸ್ ಲಾ ಆಫ್ ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ the total pressure will be the sum of the partial pressures of each component. ಈಗ ನಮ್ಮ ಹತ್ರ ಇರೋದು ಎರಡೇ ಕಾಂಪೊನೆಂಟ್, ಹಾಗಾಗಿ total pressure will be total pressure should be the sum of the partial pressures of these two component alva. So P should be equal to PA plus PB alva. P should be equal to PA plus PB. Okay, so but what is PA? PA and ಹೇಳಿದ್ರೇನು? It is PA naught into XA. So write it as P is equal to PA naught into XA. And similarly, what is PB? PB is equal to PB naught into XB. Yes, substitute that here. So P will be equal to PA naught into XA plus PB naught into XB. ಈಗ ನಮ್ಗೆ ಬೈನರಿ ಸೊಲ್ಯೂಷನ್ ಅಂತ ಆದಾಗ ಗೊತ್ತಿದೆ ಏನು ಎರಡೇ ಕಾಂಪೊನೆಂಟ್ ಇರೋದು. ಸೊ ಮೋಲ್ ಫ್ರಾಕ್ಷನ್ ಕಾನ್ಸೆಪ್ಟ್ ಪ್ರಕಾರ ಏನು, ಮೋಲ್ ಫ್ರಾಕ್ಷನ್ಸ್ ಆಫ್ all the components, sum of mole fractions of all the component will be 1. When we have only two component, therefore XA plus XB should be equal to ಎಷ್ಟಾಗ್ತದೆ, we have only two component, therefore sum of these two mole fraction should be equal to 1. So XA plus XB should be equal to 1 alva. So now ಏನು ಈಗ ನೋಡಿ ಈ equation ಅನ್ನ if you look at this equation carefully, what are the variables present here? One is P, pressure vary ಆಗ್ತದೆ alva. Anantra PA naught, does it vary? No, it is a constant. XA, does it vary? Yes, definitely XA will vary. Mole fraction may vary. 10% ಇರ್ಬೋದು, 20% ಇರ್ಬೋದು, 30% ಇರ್ಬೋದು. ಮಿಕ್ಸ್ಚರ್ ಅಲ್ಲಿ ನೀವು ಎಷ್ಟು ಹಾಕ್ತೀರೋ ಅದರ ಮೇಲೆ ಅಲ್ವಾ. PA ನಾಟ್ ವೇರಿ ಆಗ್ತದ? ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಆಫ್ ದ ಸಬ್ಸ್ಟೆನ್ಸ್ ಇನ್ ದ ಪ್ಯೂರ್ ಫಾರ್ಮ್, ಡಸ್ ಇಟ್ ವೇರಿ? ನೀವು 10 ಗ್ರಾಮ್ ಆದ್ರೂ ತಗೊಳ್ಳಿ, 20 ಗ್ರಾಮ್ ಆದ್ರೂ ತಗೊಳ್ಳಿ, ಅದರ ಪ್ಯೂರ್ ಫಾರ್ಮ್ ಅಲ್ಲಿ ವೇಪರ್ ಪ್ರೆಷರ್ ವಿಲ್ ಬಿ ಸೇಮ್ ಅಲ್ವಾ. ಸೊ PA ನಾಟ್ ವಿಲ್ ನಾಟ್ ವೇರಿ. ಅದೇ ರೀತಿ PB ನಾಟ್ ಮತ್ತೆ XB ಅಲ್ಲಿ ಡಸ್ PB ನಾಟ್ ವೇರಿ? ಇಲ್ಲ, ಬಿಕಾಸ್ ಇಟ್ ಇಸ್ ದ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ಕಾಂಪೊನೆಂಟ್ B when it is in the pure form. So again, whether you take 10 gram, 20 gram, 30 gram, it will not matter. Therefore, PB naught will not vary. And XP, does it vary? Yes, definitely. It is a mole fraction. If you take 10% solution, it is different. If you take 20% solution, it is different. So XB will vary. So this equation anna ನಾವು ನೋಡಿದ್ರೆ careful ಆಗಿ, P is a variable because it is a sum of these two. So it is a variable. Anandra XA is variable, XB is variable. There are three variables alva. So now ಯಾವುದನ್ನ equation ಅನ್ನು simplify ಮಾಡುವಾಗ we need to keep the variables as minimum as possible. Okay, so ಅದಕ್ಕೆ we know that XA plus XB equal to 1. So now let us write XB in terms of XA. ಹೇಗೆ ಬರಿಬಹುದು? XA plus XB equal to 1 ಆಗಿರೋದ್ರಿಂದ we can write XA, XB ಅನ್ನ ಆ ಕಡೆ ತಗೊಂಡು ಹೋದ್ರೆ. Okay, so let us write XA in terms of XB. So if we take XB to the other side of the equation, equality sign, then it becomes XA will be equal to 1 minus XB. Correct? Yes, now substitute. XA ಗೆ ಇದನ್ನ substitute ಮಾಡಿ. XA will be equal to 1 minus XB. So let us write XA as 1 minus XB in this equation, parent equation. So P total will be equal to PA naught, right? PA naught into, in place of XA, right, 1 minus XB. So it is 1 minus XB plus PB naught into XB. So now we have only two variables. One is the P variable and the other one is the XB variable. So now simplify it. So if we further simplify, then we will get multiply this equation by PA naught the outside. Okay, so it will be PA naught plus it will be PA naught minus PA naught into XB plus PB naught into XB. So XB is a common factor. We can remove that outside. Therefore, it will become XB into, this has positive sign. So let us write that first. So it will be PB naught minus PA naught. Clear? Therefore, P total will be equal to P total will be equal to PA naught plus XB into PB naught minus PA naught. Right? So, this is the expression for total vapor pressure of a system containing a system made up of two volatile liquids. Okay. So, now if we look at what are the variables, one is this P is the variable and the other one is this XB is the variable. Rest, this is a constant and this also is a constant. ಹಾಗಾಗಿ ಇದನ್ನ ಕೇರ್ಫುಲ್ ಆಗಿ ಈಕ್ವೇಶನ್ ಅನ್ನು ನೋಡಿದ್ರೆ how does it look like? Say, let me replace this variable P by Y, then it will be Y is equal to some constant, let me write it as C plus again one variable, let me write it as X and multiplied by some one more constant M. Alva, so it is in the form Y is equal to mx plus C. Alva, what does this equation indicate? It indicates a equation of a straight line. Alva, mathematically this is equation of a straight line. Therefore, if we plot vapor pressure, variable yaudu vapor pressure against one more variable is the mole fraction. Mole fraction ige plot madidre. If we plot vapor pressure against the mole fraction, then we should get a straight line. Clear? So the solution, vapor pressure of the solution idu. Okay, idu vapor pressure of the solution will be, so ಈಗ y equal to mx plus c ಅಂತ ಹೇಳಿದ್ರೆ, c ಅಂತ ಹೇಳಿದ್ರೆ ಏನು? It is the y intercept ಅಲ್ವಾ? m ಅಂತ ಹೇಳಿದ್ರೆ ಅದು slope. So therefore the plot will be, for the solution it will be something like this. There is some intercept, so it will come straight line. It will be something of this form, a straight line. Okay, so now mole fraction anta heluvaga, mole fraction we can write in terms of A, component A, ಅಥವಾ we can also write in terms of component B. So let us write XA equal to 1. So we are along the x-axis we are plotting the mole fraction. So let us say here at this point mole fraction of the component A is 1 ಅಂತ ಹೇಳಿದ್ರೆ pure A exists at this point. Okay, so corresponding vapor pressure will be ಅಲ್ಲಿ ಒಂದೇ component ಇದ್ದಾಗ ಅದರ pressure will be pure A ದು pressure. So it is P not A. Correct ಅಲ್ಲ? ಅದೇ ರೀತಿ ಅಂದ್ರೆ ಅದು ಪ್ಯೂರ್ ಫಾರ್ಮ್ ಅಲ್ಲಿ ಇದೆ ಅಂತ ಹೇಳಿದ್ರೆ ಮೋಲ್ ಫ್ರಾಕ್ಷನ್ ಆಫ್ ಬಿ ವಿಲ್ ಬಿ 0. ಕರೆಕ್ಟ್? ಅದೇ ರೀತಿ y ಆಕ್ಸಿಸ್ ನ ಅದರ್ ಎಂಡ್, ಲೆಟ್ ಅಸ್ ಸೇ x ಅದರ್ ಎಂಡ್ ಅಲ್ಲಿ ಏನು, ಮೋಲ್ ಫ್ರಾಕ್ಷನ್ ಆಫ್ ಬಿ ಇಸ್ 1 ಅಂತ ಹೇಳಿದ್ರೆ ಬಿ ಪ್ಯೂರ್ ಫಾರ್ಮ್ ಅಲ್ಲಿ ಇದೆ. ಸೊ ವೇಪರ್ ಪ್ರೆಷರ್ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಟು ದ ಇಂಟರ್ಸೆಪ್ಟ್ ವಿಲ್ ಬಿ therefore PB naught. It is the vapor pressure of pure B. Anantara, so therefore XA will be equal to 0. So if we are plotting partial pressure of A, okay, so partial pressure of A, so initially ishtirtade, anantara A du component ಕಮ್ಮಿ ಆದ ಹಾಗೆ ಅದು decrease ಆಗ್ತದೆ. Then it becomes 0 mole fraction, partial pressure also will be 0. Pressure due to the component A will also be 0. ಅದೇ ರೀತಿ ಈ ಪಾಯಿಂಟ್ ಅನ್ನ ನೀವು ತಗೊಂಡ್ರೆ it is a partial pressure due to B. So adra mole fraction kammi aagta banda hage it will go on decreasing, 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 decreasing. And when the mole fraction becomes zero, mole fraction of that component becomes zero, the partial pressure due to it will also be zero. Okay, so it will pass through the origin here. ಅದೇ ರೀತಿ ಇದು equation ಇದು ಕೂಡ ಅಷ್ಟೇ, it will pass through the origin. So ಇದೇನು ಇದು ಡಾಟೆಡ್ ಲೈನ್ ಅಲ್ಲಿ ಎಕ್ಸ್ಪ್ರೆಸ್ ಏನ್ ಮಾಡಿದ್ದಾರೆ ನೋಡಿ, ದಟ್ ಇಸ್ ದ ಪ್ರೆಷರ್, ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಆಫ್ ಕಾಂಪೊನೆಂಟ್ ಎ ಅಥವಾ ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಆಫ್ ಕಾಂಪೊನೆಂಟ್ ಬಿ. ಅದೇ ಇನ್ನೊಂದು ಈ ಲೈನ್ ಏನಿದೆ ಇದು that represents the total vapor pressure of the solution. Okay, total vapor pressure of the solution, which is equal to XA into PA naught plus XB into PB naught. Clear? Yes. So that is about the partial pressure. Raoult's law. So this is applicable only when two volatile liquids form a homogeneous mixture. And similarly, it is valid only for ideal solutions. Ideal solution ಗೆ ಮಾತ್ರ ಈ Raoult's law ಅಥವಾ Raoult's law the equation applicable ಆಗ್ತದೆ. And mole fraction of each component is different in the liquid and its vapor phase. So ಅಲ್ಲಿ Raoult's law ದಲ್ಲಿ ನಾವು ಹೇಳುವಾಗ ಏನ್ ಹೇಳ್ತೇವೆ, it is the for a solution of volatile liquid, the partial pressure of each component in the vapor phase is directly proportional to the mole fraction of the respective component in the solution phase. Okay, so now mole fraction. So ಕೆಲವು ಮಾಲಿಕ್ಯೂಲ್ಗಳು ವೇಪರ್ ಫೇಸ್ ಅಲ್ಲಿ ಇರ್ತದೆ, ಕೆಲವು ಮಾಲಿಕ್ಯೂಲ್ಗಳು they will be in the liquid phase. So there will be a mole fraction, a fraction of the molecule in the vapor phase also. So the fraction of the molecule in the vapor phase, it is different from the fraction of the molecules in the liquid phase. So if suppose Ya and Yb are the mole fraction of the components A and B respectively in the vapor phase ಅಲ್ಲಿ ಅದರ ಕಾಂಪೊನೆಂಟ್ ಮೋಲ್ ಫ್ರಾಕ್ಷನ್ ಗಳು A ಮತ್ತೆ B ಇದ್ದು, if it is Ya and Yb, then from the Dalton's law we have Pa is equal to Ya into P total, and similarly Pb equal to Yb into P total. Clear? This equation is very important for your competitive examination point of view and even for the board exam also. Okay, clear? Vapor phase ಅಲ್ಲಿ ಮತ್ತೆ liquid phase ಅಲ್ಲಿ mole fraction same alla. Okay, mole fraction in the vapor phase is calculated using this equation, that is a Dalton law. Clear? So according to which Pa is equal to Ya into P total, and similarly Pb is equal to Yb into P total. ಅದೇ ನಮ್ಮ ಲಿಕ್ವಿಡ್ ಫೇಸ್ ಅಲ್ಲಿ ಆದಾಗ ಏನಾಗ್ತದೆ, Pb is equal to XB into Pb naught. ಅದೇ ಒಂದು ವೇಳೆ Pa ಆಗಿದ್ರೆ it will be XA into Pa naught ಅಲ್ವಾ. ನೋಡಿ ಇಲ್ಲಿ ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ದ ಕಾಂಪೊನೆಂಟ್ ಇದು. Clear? Where this is a mole fraction in the liquid phase. ಅದೇ ರೀತಿ this is the mole fraction of component B in the liquid phase. Clear? So that it is Pa, partial pressure will be equal to Pa naught into XA, Pb equal to Pb naught into XB. Adhe, if it is the mole fraction in the vapor phase, then it is Pa will be equal to Ya into P total. Okay? Or Pb will be equal to Yb into P total. Okay? Keep this in your mind, this difference. Okay, therefore, in general, Pi will be equal to, in the vapor phase. So, in the vapor phase, Pi will be equal to mole fraction, this has to be Y, so since we have written this as Y, so actually we should have written this also as Y, that would be more better. There will not be any confusion. So, it will be Yi into P total. Okay. So Pi will be equal to Yi mole fraction of it, because In general, when we say mole fraction, we write x. Therefore, it has been written as x. But in order to avoid the confusion, I am writing it as y. yi into P total, where y is the mole fraction of the component I in the vapor phase. Clear? P total. Okay. So now, Henry's law, if we take, what does Henry's law state? Partial pressure of the gas in the vapor phase. So remember, Henry's law is applicable to a system in which gas is dissolved in a liquid. Right? So, adra prakara, partial pressure of the gas in vapor phase is proportional to mole fraction of the gas in the solution. So, P is equal to Kh into X. Ade Raoult's law prakara, partial pressure of each component of the solution, partial pressure of the Henry's law, partial pressure is proportional to mole fraction of the solution, so that P is equal to Kh into X. Aita? Ade Raoult's law nodidre, partial pressure of each component of the solution is directly proportional to its mole fraction in the solution. So statement appears to be same. So it is Pi is equal to Pi naught into Xi. Correct? So if we compare both, what difference do we observe? Partial in both the cases, partial pressure of a volatile substance. When I say gas, it is the highly volatile. Correct alla? Liquid anta helidaga ನಾನು ಇನಿಷಿಯಲಿ ನಿಮಗೆ ಹೇಳಿದ್ದೇನೆ ಏನು ಲಿಕ್ವಿಡ್ ಅಲ್ಲಿ ನಾವು ಇನ್ ಜನರಲ್ ನೋಡೋದಾದ್ರೆ ಎರಡು ಬರ್ತದೆ, ಒಂದು ವೊಲಟೈಲ್ ಲಿಕ್ವಿಡ್, ಇನ್ನೊಂದು ನಾನ್ ವೊಲಟೈಲ್ ಅಂತ ಹೇಳುವಂತದ್ದು. ಸೊ ನಾವಿಲ್ಲಿ ಡಿಸ್ಕಸ್ ಮಾಡ್ತಾ ಇರೋದು ವೊಲಟೈಲ್ ಮಿಕ್ಸ್ಚರ್ ಗಳನ್ನೇ. ಓಕೆ, ಸೊ ಆ ವೊಲಟೈಲ್ ಮಿಕ್ಸ್ಚರ್ ಗಳಲ್ಲಿ ವೊಲಟೈಲ್ ಲಿಕ್ವಿಡ್ ಅನ್ನು ತಗೊಂಡಾಗ ಪಾರ್ಷಿಯಲ್ ಪ್ರೆಷರ್ ಆಫ್ ಈಚ್ ಕಾಂಪೋನೆಂಟ್ ಇಸ್ ಪ್ರಪೋರ್ಷನಲ್ ಟು ಇಟ್ಸ್ ಮೋಲ್ ಫ್ರಾಕ್ಷನ್. ವೆನ್ ಐ ಸೇ ಗ್ಯಾಸ್ ಹ್ಯಾಸ್ ಬಿನ್ ಡಿಸಾಲ್ವ್ಡ್ ಇನ್ ಅ ಲಿಕ್ವಿಡ್, ಅದರಲ್ಲಿ ಗ್ಯಾಸ್ ಅಂತ ಹೇಳಿದ್ರೇನು, ಇಟ್ ಈಸ್ ಹೈಲಿ ವೊಲಟೈಲ್ ಅಂತ. ಅಂದ್ರೆ ಈ ಲಿಕ್ವಿಡ್ ಏನಿದೆ, ವೊಲಟೈಲ್ ಲಿಕ್ವಿಡ್ ಏನಿದೆ, ಅದರ ಎಕ್ಸ್ಟ್ರೀಮ್ ಕೇಸೇ ಗ್ಯಾಸ್ ಅಲ್ವಾ. It is completely existing in gas, highly volatile, completely volatile, I can say. Right. So, the partial pressure of, so if we compare both, so by comparing both, it can be concluded that the partial pressure of a volatile liquid or a gas is proportional to mole fraction in the solution. So, where does the difference exist? Difference exists only in the proportionality constant, that is Kh and Pi. Correct alla? The equation ಅನ್ನೇ ನಾವು ನೋಡಿದ್ರೆ ನಮಗೆ ಡಿಫರೆನ್ಸ್ ಕಾಣುವಂತದ್ದು ಎಲ್ಲಿ, ಈ ಕಾನ್ಸ್ಟೆಂಟ್ ಗಳಲ್ಲಿ ಮಾತ್ರ, Kh ಮತ್ತೆ Pi naught. So Raoult law is the special case of Henry's law, okay, in which Kh is equal to Pi naught ಅಲ್ವಾ. Henry's law ಅದು ಅದರದ್ದು ಒಂದು ಎಕ್ಸ್ಟ್ರೀಮ್ ಕಂಡೀಷನ್ ಅಂತ ಆದ್ರೆ, Raoult law ಅದರಲ್ಲೇ ಒಂದು ಸ್ವಲ್ಪ ವೊಲಟೈಲ್ ಆದಾಗ ಅದರದ್ದು how does the equation change? ಆ ರೀತಿ ಬರ್ತದೆ. Therefore, it is a special case of Henry's law, okay, in which Kh becomes equal to Pi naught. ಅಷ್ಟೇ. Clear? Yes. So now, based on this, let us discuss few numerical problems. So let me take up first one. Heptane and octane form an ideal solution. I said Raoult law is applicable to ideal solutions only. Okay. So heptane and octane form an ideal solution. At 393 Kelvin, sorry, this has to be capped. Okay, so at 373 Kelvin, the vapor pressure of two components are 105.2 kilopascal and 46.8 kilopascal respectively. What will be the vapor pressure of a mixture of 26 gram heptane and 35 gram octane? So, what do we have to calculate? What will be the vapor pressure of a mixture anta kelidare. Therefore, we need to calculate P total. Correct? P total gottilla. P total ಎಷ್ಟು ಅಂತ ಹೇಳಿ ನಾವು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬೇಕು. ಆನಂತರ ಏನ್ ಕೊಟ್ಟಿದ್ದಾರೆ? ವೇಪರ್ ಪ್ರೆಷರ್ ಆಫ್ ಟೂ ಕಾಂಪೋನೆಂಟ್ಸ್ ಏನು, ಹೆಪ್ಟೇನ್ ಅಂಡ್ ಆಕ್ಟೇನ್ ಆರ್ 105.2 kilopascal and 46.8 kilopascal. So 105.2 kilopascal is the vapor pressure of heptane, pure vapor pressure of pure heptane. Therefore, it is P naught of heptane. Okay, ananತರ ಇದು 46.8 kilopascal is octane ಇದ್ದು. Therefore, it is P naught of octane. Octane. Okay, so now we have to find out the total vapor pressure. So from Raoult's law, we know P octane is equal to mole fraction of the octane into P naught of octane. ಅದೇ ರೀತಿ P heptane is equal to X into, mole fraction of heptane into P naught of heptane. First of all, P total ಅಂದ್ರೆ ಏನು? P total should be P of heptane, partial vapor pressure of heptane plus partial, okay, let me write a small letter P only to avoid all the confusions. So partial pressure of heptane plus partial pressure of octane. But what is partial pressure of heptane? Partial pressure of heptane will be mole fraction of heptane into P naught of heptane. ಅದೇ ರೀತಿ what is partial pressure of octane? Partial pressure of octane will be mole fraction of octane into P naught of octane. ಅಲ್ವಾ? ಸೊ ನಮಗೀಗ P naught ಕೊಟ್ಟಿದ್ದಾರೆ. Mole fraction we have to find out. So mole fraction ಗೆ what is the formula? Mole fraction is of any component will be equal to n of x of a ಅಥವಾ x of 1 will be equal to n of a divided by n of a plus n of b. Okay? N of b. So what is n there? It is the number of moles. So number of moles ಅನ್ನು ಹೇಗೆ calculate ಮಾಡ್ತೀರಿ further? So number of moles of any substance will be equal to weight of the substance divided by the molecular weight ಅಥವಾ molecular mass. So first we have to weight ಕೊಟ್ಟಿದ್ದಾರೆ ಅಲ್ವಾ? 26 gram of heptane, 35 gram of octane. ಅಲ್ವಾ? ಸೊ ನಮಗೀಗ ಮಾಲಿಕ್ಯುಲರ್ ವೇಟ್ಗಳು ಬೇಕು ಹೆಪ್ಟೇನ್ ಮತ್ತೆ ಆಕ್ಟೇನ್. ಸೊ ಮೋಲಾರ್ ಮಾಸ್ ಆಫ್ ಆಕ್ಟೇನ್ ವಿಲ್ ಬಿ ಆಕ್ಟೇನ್ ಇಟ್ ಇಸ್ ಆಲ್ಕೇನ್ ಅಲ್ವಾ? CnH2n+2. ಸೊ ಆಕ್ಟಾ ಅಂತ ಹೇಳಿದ್ರೆ ಇಟ್ ಇಸ್ 8, ಸೊ ಇಟ್ ಇಸ್ C8H16+2, right? So it is C8H18. So if we calculate atomic mass of carbon is 12, so it is 8 into 12 plus there are 18 hydrogen, so 18 into 1. The atomic mass of hydrogen is 1, so it comes out as 114 gram per mole. ಅದೇ ರೀತಿ if we calculate the molar mass of heptane, so heptane molar mass, heptane anta helidre again it is a alkane, so it is 7. Hepta means 7 alba. So C7H16 it has to be CnH2n+2. So n is 7 here, therefore it is C7H16 alba. So 7 into 12, 7 carbon into its atomic number, that is atomic mass, that is 12 plus 1 into how many hydrogens are there? 16. Therefore it is 1 into 16, therefore it is 100 gram. So molar mass of octane is 114 and molar mass of heptane is 100. Clear? Therefore number of moles of octane will be n divided by molar mass. So mass of octane is 35 gram. So it is 35 divided by 114. Therefore it comes out as 0.31. Number of moles of heptane. Again n divided by W. So NH2 heptane H2, it is 26 gram. Ala? Therefore 26 divided by molar mass of heptane H2, it is 100. Therefore it is comes out as 0.26. Clear? Yes. Now calculate the mole fraction of octane. So mole fraction of octane will be number of moles of octane divided by number of moles of octane plus number of moles of heptane. So number of moles of octane is 0.31, number of moles of heptane is 0.26. Allah. So 0.31 divided by 0.31 plus 0.26, therefore it comes out as 0.544. ಒಂದ್ರದ್ದು ಗೊತ್ತಾದ್ರೆ ನಮಗೆ ಮೋಲ್ ಫ್ರಾಕ್ಷನ್, ಇನ್ನೊಂದ್ರನ್ನ we can calculate 1 minus x ಅಲ್ವಾ. So yes, if we calculate we get 0.456 as the mole fraction of heptane. So now calculate pressure due to octane, pressure, partial pressure due to heptane. Partial pressure due to octane will be mole fraction of it into P naught of it. And heptane will be mole fraction of it into P naught of it. Pure like this. So octane will be, partial pressure of octane will be 0.544 into 46.8 kilopascal. Okay, it comes out as 25.46 kilopascal. And P heptane will be 0.456 into 105.2 kilopascal, and hence it comes out as 47.97 kilopascal. Therefore, total vapor pressure will be P total will be equal to P octane plus P heptane. So add both. So it is 25.46 plus 47.97, and hence it comes out as 76.43 kilopascal. Clear? Yes. So now let us go through one more problem. The vapor pressure of ethanol and methanol are 44.5 millimole, 5 mm of Hg mercury, that is, and 88.7 mm Hg respectively. So vapor pressure of ethanol is so much. So this is vapor pressure of ethanol, pure ethanol. Therefore it is, I can write it as P naught of ethanol. E, let me write. And this is vapor pressure of methanol. Therefore it is P naught of methanol. Let me write it as P naught of, yeah. An ideal solution is formed at the same temperature by mixing 60 gram of ethanol. So weight of ethanol is 60 gram and 40 gram of methanol. So weight of methanol is 40. Calculate the total vapor pressure of the solution. So this is also similar to the earlier problem. So first calculate the number of moles of total vapor pressure. As I said earlier, total vapor pressure should be equal to, therefore now it should be equal to P of ethanol plus P of methanol. Correct alla? So P of ethanol anta helidre eno? It is P naught of ethanol P naught of ethanol into XA of ethanol. Alva. So namige first XA. Adhe riti P naught, P of methanol will be P naught of methanol into X of methanol, mole fraction of methanol. So first mole fraction beku. Mole fraction again, what is the formula? Mole fraction will be equal to number of gottide NA divided by NA plus NB. Okay, but what is N? It is weight of the substance divided by molar mass. Okay, yeah. So number of moles of ethanol will be weight of the substance. Yes, 260 gram kottidare, 60 gram divided by molecular weight of the ethanol. Formula, what is the formula of ethanol? It is CH3 CH2 OH. So how many carbons are there? There are 2 carbons. So it is 2 into 12 plus. How many hydrogens are there? 3 plus 4 plus 1. So there are 6. So 6 into 1. So it is 6 plus. How many oxygen is there? There is 1 oxygen. Therefore, 1 oxygen atomic mass is 16. Therefore, it is 2 into 12. That is 24 plus 6. That is 24 plus 6 will be 30. Yeah. Plus oxygen. It is 40. 30 plus 46 it has to be. Okay. Okay. Calculate. Okay, so then you will get the number of moles of ethanol. Similarly, calculate the number of moles of methanol. So what is the formula of methanol? Formula of methanol is CH3OH. So how many carbon? There is 1 carbon, so it is 12. Then how many hydrogens? There are 4 hydrogens, so it is 4. And how many oxygen? There is 1 oxygen, so it is 16. Therefore, it will be 20 plus 30. It has to be 32. Clear? Yes. So, therefore, number of moles of methanol will be mass of methanol. It is 40. 40 divided by 32. So, it comes out as, calculate, whatever, 1.25. So, now mole fraction of methanol, if we consider 1.25, yes, this comes out as 46 if we write, it comes out as 1.3. Okay, so mole fraction of methanol will be number of moles of methanol divided by number of moles of methanol plus number of moles of ethanol. So 1.25 plus divided by 1.25 plus 1.3, and hence it comes out as 0.4545. So mole fraction of ethanol, therefore we can calculate 1 minus so much. So it comes out as 0.545. Okay. So now therefore total pressure of the solution will be equal to XA into PA naught plus XB into PB naught. Therefore mole fraction of methanol is 0.4545. Therefore 0.4545 into pressure of methanol. Pressure of methanol is 88.7. Therefore into 88.7 plus mole fraction of ethanol is 0.545 and its vapor pressure is 44.5. Therefore, if you substitute, you will get 64.58 mm of mercury. Clear? Yes. So, in today's class, we have discussed about the solution which is a liquid in liquid where two volatile liquids are mixed. And then about the vapor pressure we have discussed because it is a volatile liquid, and then the factors that affect the vapor pressure also we have discussed, and then we discussed about the Raoult's law which is applicable to a mixture of volatile liquids, and the problems based on volatile this Raoult's law we have discussed, and similarly in the beginning we discussed some numerical problems related to the Henry's law. I hope it is clear to you. Thank you students for watching.